So, last time we talked about eigenvalues, eigenvectors. Today we're going to use them. See? No waste in this class. We use everything. Every part of the lecture, we use it. Okay. No other part of the lecture is like cutting up an animal, though. It's the only aspect. Okay, so diagonalizing basis is what I call this. It is useful to transform a system's state vector x into a special basis that diagonalizes, that is, leaves non-zero components only along the diagonal, the system's A matrix. So, you know our good old-fashioned A matrix. It's got, like all kinds of different things in it. Say like that. It's like a weird blue color. There we go. A diagonal one, that's 2 by 2, might look like, I don't know why I want to write 17 so much. Might look like this. Okay, that would be a diagonal one. Only non-zero components are along this diagonal. So, I say that we can do that for most A matrices. We can change bases, and that changes what our state variables are. But like I said before, when we introduced state variables are not unique. The number of state variables is. So the number doesn't change, but you can change what they are. So for instance, you could go from a basis in which one of the state variables is the voltage across a capacitor to another basis where one of the state variables is actually representing the voltage across a capacitor plus 3 times the voltage across a resistor or something like that, for instance. That would be a possible basis change. Why we're doing that is not quite clear, but it is useful, and we're going to use it at the end of this lecture too. So for systems with n distinct eigenvalues, to which we limit ourselves in this discussion, this is always possible. So I'm going to assume when we do this in this class that I'm only going to give you, or you can assume that I'm only going to give you matrices that have distinct eigenvalues. So there are no repeated eigenvalues. In diagonalized form, it will be relatively easy to solve for the state transition matrix, which is why we're doing this. I mean, it's one of the reasons. Having a diagonalized state space representation is actually useful for some other reasons, but our main motivation right now is to find the state transition matrix, which, as you might recall, and as your homework may be proving to you, finding the state transition matrix from the definition, the series definition, is not that fun. So this is the preferred way. So this is why I'm introducing this here. So the first thing we have to consider is how to change basis in the state equation at all. Okay, we're going to pick a very specific basis in a moment, but we want to first know how to do it at all. So let's figure out how to change the basis in the state equation. As with all basis transformations, the one we seek can be written like so. So the original x vector is equal to P, which is called the transformation matrix, times x prime, which is our new vector in the new basis. Okay? So we say that x prime is a representation of the state vector in a new basis. Now, depending on how rigorous your linear algebra was, there is a distinction between the components of a vector and its basis, and I see smiles. Components of a vector and its basis. And what we're doing is we're just assuming that we're looking at column vectors, as we call them, column vectors, which are the component representations of the vector. Okay. Okay. So this is familiar if you've ever done matrix vector multiplication, but it might be new, may or may not be new to you, that this changes the basis of a vector, and it in fact does do so. So substituting this transformation into the standard linear state model equations yields the model. So we just plugged it into our old, x dot equals ax plus bu, but we plugged in x equals p x prime. We're using prime here, so I want to I know that this notation might be a little weird. Prime is not used here to denote a derivative. Okay, we are using dot to denote a derivative in this expression, but we're not using prime to denote derivative. We're just saying another a vector, or actually a vector represented in another basis. Okay. Okay. So in the primed basis, or I guess that's one way to call it, the primed basis, x prime dot is equal to, this is the new A matrix, right? Whatever shows up here is the new A matrix. So it has the transformation matrix in it twice, and the original A matrix. So if you take the original A matrix and you left multiply it by the transformation matrix inverted, right multiply it by the transformation matrix, you get your new A matrix, which we call A prime. And it's pretty straightforward. I mean, yeah. And then the B matrix, you just hit it with P inverse, and you get the new B matrix, B prime. C matrix, C times P, and then the D matrix, it turns out, doesn't change at all. So D prime is equal to D. Okay. So now we know what to do if we're going to change basis for our state vector, right? So we know 215 gives us what that looks like. Yeah?
What would be a representation of the inverse of a transformation matrix? They just flip upside down, or one
so matrix inverse. Matrix inverse is this, there's a matrix, and then you do the -1. Matrix inverse. It's a topic that there is quite a bit involved in it, and you'll get more in depth in that if you haven't seen it yet in linear algebra. But if our original matrix is P, you can think of P as being something that operates on x prime and gives you back x. And if this was a scalar equation, then you would, if you wanted to solve for x prime, you would take the reciprocal of, if P was a scalar, you would just take the reciprocal of P, multiply both sides, or alternatively, divide both sides by P, right, to solve for x prime. But we can't do that when P is a matrix. We have to instead left multiply, because the order of multiplication and matrix multiplication matters, right? Left multiply by P inverse on both sides. So P inverse is defined as the matrix that makes this true. So, well, I should write one more step, right? P inverse times P x prime. So by definition, P inverse times P is the identity matrix. And therefore, we can say that that the right-hand side of this is x prime. So it's just like the reciprocal, but for a matrix. But you can't just simply take the reciprocal of each element of the matrix. There's an operation that goes into taking that inverse, and you do need to go through that. Yeah.
Sorry, I lost the train of thought. I was gonna ask before you explain that why they bother to write out the inverse of p times p, because when they cancel each other out.
Oh, I just did it just to make sure that we knew that that was what was happening there. You don't often.
They only cancel each other out if they're touching. The P inverse AP, those both operate on. They don't cancel each other out.
You mean here?
In between them.
Yeah. So here, because the order of matrix multiplication matters, you can't cancel P inverse and P because there's a matrix in between. If they're operating on each other, then they're directly operating together, and then one does something and the other one just undoes it. So it's the same as just multiplying it by the identity matrix. So I do realize that there is some struggle here with the linear algebra aspect, and I can do maybe like a little primer on that for you guys, like a bonus lecture if you guys want. Now I can't, because we're like already, like we're already doing this. We're already doing this. So I will, if you guys ask me to, I will do a little like video primer on how to do some of these things. The thing that I don't require that you guys do a whole lot of this manipulation on a high level on your own. Like we derive these expressions and then you have to just essentially plug stuff into them. So you have to be able to take the inverse by hands of, like for instance, up to a 3x3 matrix. But just like with the determinant, it's pretty formulaic. So if you don't understand it in detail now and you just learn how to do the operation, that's okay, and then later you'll get a little bit more understanding. So it's I'm giving you guys. I'm not requiring that you guys understand linear algebra at a deep level. What I'm really doing is I'm asking you guys to use some linear algebra operations. If you understand it at a deep level, it helps a lot. But if you don't, you can just use the operations, and I don't require that you do a whole lot of derivation in linear algebra. So like I wouldn't require you guys to be able to derive 2.15a on an exam, for instance. That wouldn't be something I would require. Although it's really not that bad, but if you're not familiar with linear algebra, it is that bad, right? But if you are familiar with it, it's not too bad to do. Okay, so we'll move along with our limited, sometimes in some ways, linear algebra, but we'll recognize that once we see these results, like 215a, we should be able to do things like invert a small matrix up to a 3x3 and multiply matrices together. Like those are the types of things that I'm expecting you guys to be able to do. Not necessarily understand all the details of a derivation in linear algebra stuff. Although it would be nice, for those of you who have taken it, I expect you guys can follow that. Okay, so modal and eigenvalue matrices. This is just a definition. So let a state equation have matrix A with n distinct eigenvalues lambda I and eigenvectors mi. Let the eigenvalue matrix lambda, this is capital lambda, be defined as, whoa, that was really big, maybe a smaller lambda. Lambda equals, it's a diagonal matrix with the eigenvalues along the diagonal. And everything else in the matrix is 0. So this is shorthand for everything else in the matrix is 0. I don't write out a bunch of zeros and dots just because I did at first when I wrote this, and I was like, this looks harder to understand than easier to understand. So, okay. So the eigenvalue matrix. Furthermore, the modal matrix M, let it be defined as a matrix composed of all the eigenvectors. So this is kind of a strange notation if you haven't seen it. It's meant to be helpful, but if it's confusing, don't worry about it. It's not really. These bars here are just meant to recognize that M1, M2, etc., all these eigenvectors are column vectors. And so what we're doing is we're creating a matrix out of a bunch of column vectors. We're just sticking them into a matrix, okay?
The whole column is the 1.
Yeah, that's right. So M might look, if it was a 2 by 2, M might look like 1, 7, 6, 5, where M1 was 1, 7, and M2 was 6, 5. So we just took these guys and just stuck them in there. And this is now our M matrix. So the eigenvalue matrix and the, what sometimes we call it eigenvector matrix, which is also called the modal matrix, is really just matrices made up of our eigenvalues and eigenvectors, right? Some extra zeros thrown into the eigenvalue matrix. And this is really, really useful for a lot of different things, and we can only touch on a little bit of it. But I will say a little aside. So when you're working out homework problems, I encourage you to try stuff out in MATLAB and check things, especially in MATLAB. I want you guys to be able to do smaller problems by hand so you can do them on the exams, obviously. But using MATLAB is really useful. When I told you the other day that you can find the eigenvalues and eigenvectors in MATLAB using the Eig function, what I didn't tell you is that the Eig function actually returns lambda and M. It returns two matrices, lambda and M. So it doesn't even return just like a list of the eigenvalues or whatever. I think you can ask it for just a list or a list of the eigenvectors. It gives you the modal matrix M, and it gives you the eigenvalue matrix lambda. So that's useful. It also makes it super easy for us. They know, MATLAB knows what we're going to do with it. So it's smart like that. Okay. Yeah, question.
In the M, those M1 and 2 and Mn, are those eigenvalues or eigenvectors?
These are eigenvectors. So the eigenvalues are the lambdas, and the m's are the eigenvectors. And then the boldface font, I don't know how well it shows up on the screen, but the boldface is supposed to denote the vector. And when I write it, I draw the little arrow over it. Okay. So when I was growing up, I grew up near Pullman, Washington, where Washington State University is. I would go to their basketball games sometimes, and they had this couch courtside where if you won a door prize or whatever, you could sit and watch the game in the couch. And Aaron in the front row right here, just with his own table. Everybody else crammed into their own little desk, and it's like Aaron every day wins the door prize. He gets to sit on the couch in the front row. So congratulations. Okay. So now we've got a couple pieces. So what have we done so far? We learned how to change the basis of a state space model, right? The state equation and the output equation. We learned what the modal and eigenvalue matrices are, okay? And now we're going to put those two things together, and you guessed it, we're going to let the modal matrix M be the transformation matrix for our state model. That means just using M instead of P in the previous expression for x prime, M inverse times x gives us our x prime. The state equation becomes this expression here, 217. Now, this is, this is our transformed state model, right? This is our A prime. But let's see if we can find out something interesting if we go on a little derivation. Yeah. Oh, oops, that was just a typo. This should be M. Good call. I missed that one. I clearly copied and pasted that and didn't replace the
Plagiarism.
self-plagiarized for my own lecture from like 10 lines above. Yeah, that's a different thing. You can copy and paste your own equation from above to below. That's allowed. Okay, the what that means is don't turn in the same essay in two different classes as if it was a new essay. That's self-plagiarism. Yeah. Everybody goes, although the rules on it are pretty murky, I will say. Okay, so the Eigen Problem implies this statement, and this statement is going to be a little trippy, but I think that you guys will be able to hang with me on this. I don't derive everything in this class, but I do occasionally like to sprinkle one in just for good measure. You guys need to have somebody to complain about, right? If I didn't do boring linear algebra derivations, who would you complain about later today?
I hear a lot of machine design bitches.
Oh man, I'm so glad I don't have to teach that class. I taught that class once. I didn't enjoy it. I mean, I like the topic. It's just teaching it's hard. Okay, so thank you. That makes me feel good. Whoever said that. The Eigen Problem implies this statement, and so let's try to unpack this a little bit. It's a little hard to parse, but remember that the Eigen Problem is AM equals lambda m, right? Where m is an eigenvector. So if we actually said for some specific eigenvalue, eigenvector pair, this would hold. Okay? So if we use this identity and we just turned it into like a massive matrix equation with all of them stuck together side by side, so that M1, M2, all the way to Mn were just stuck into, you guys know what it is, the modal matrix, right? And you put A out here, you can still do this matrix multiplication. It just turns into a big matrix, right? And the same with over here. What lambda does, its form with the diagonals, it just selects out each M1, it selects out M1, M2, etc., and it scales them and puts them in the matrix. So this is a matrix equals a matrix instead of over here it was a vector equals a vector. Now, if you hang with that, I think the rest of it The rest of it's not too bad. The rest of this derivation is not too bad. This is a common trick to do in derivations, but I think it's a little scary. At first it's a little intimidating. But all we did was we said, oh, all of these are true, these vector ones are true. We'll just turn it into a matrix version of that. And it's still true. So, okay. Now, this is the same as just saying A times the modal matrix is equal to the modal matrix times lambda. Okay? Because we're just saying, oh, these big M1, M2, etc. matrices are just the modal matrices. That's all we did there. So, if that's true, let's go ahead and solve for an expression that we have up here in the motivation for what we're doing here. We could left multiply both sides of this equation by M inverse, and we would have our A prime on one side. So let's find out what is on the other side of the equation once we do that, okay? So let's left multiply by M inverse, AM. So then we have to left multiply the other side by M inverse. And this right-hand side can simplify, right? M inverse times M is just the identity matrix, and the identity matrix is just like 1, so you don't even have to write it. And we are left with lambda on the right-hand side. This is the like aha. So you guys can all be like, oh my god, this is beautiful. This is so cool. Look at that. So we discovered that A prime is equal to lambda. Not factorial. That's just excitement. Okay. So, recall that lambda is diagonal. Therefore, we have diagonalized the state space model. In full form, the diagonalized model is given below. So, the rest of them don't really have any like magical representation. They're just M inverse B, whatever. But the A matrix is diagonalized, which is pretty cool. Okay. Okay. Now, yet another step. But now we're really at the point where we're going to use it, okay? So, computing the state transition matrix. Recall our definition of the state transition matrix. Capital Phi equals E to the AT, the matrix exponential of AT. Directly applying this to the diagonalized system of equation 218, so we're going to use this expression, but with A being lambda, because we're going to do this for the diagonalized system. So our phi prime, so our prime state transition matrix, is equal to E to the lambda t. But you may recall what I call the diagonal property of the matrix exponential, or the state transition matrix, which is that if your matrix that you're taking the exponential of is diagonal, then the matrix exponential is just the scalar exponential of all of the diagonal elements along the diagonal. So that's what we have here. So instead of having some big definition to go back to and try to divine what the exponential series is, which I think you guys have a homework that asks you to do that, we can just simply say, oh, it's either the lambda 1t, e to the lambda 2t, all the way to e to the lambda nt. And remember, so our lambdas are just our eigenvalues. So this expression right here gives you the primed state transition matrix immediately upon finding the eigenvalues, which is sweet, right? That's like super easy to do. And remember, the state transition matrix is essentially the key that unlocks the entire solution for the state response and the output response. So this is a really nice expression to have. Now, in this last equality, we use the diagonal property. So recall that the free response solution to the state equation is given by the initial condition and state transition matrix. So the free response prime, so the primed state response, free response, is equal to phi prime x prime of 0. So, I should put primes here on each of these x's. But what we've done here, since I have a diagonal matrix multiplying a vector, you have each initial primed state multiplying e to the lambda 1 being the eigenvalue associated with what we would call mode 1 of the system, the first eigenvector. And then the initial state of the second state vector, or state variable at time equals 0, the initial condition of that, times e to the lambda 2t. So we've decoupled this so that each primed state variable matches up exactly with an eigenvalue exponential. Okay? It's a pretty nice little expression. We can find the primed initial conditions from the original initial conditions with that expression, just converting bases of the initial condition. So we've completely decoupled each state's free response, one of the remarkable qualities of the diagonalized system. Okay? So it's a pretty sweet deal. At this point, one could simply solve the diagonalized system for x prime. If you only cared about the free response, then this is the expression for it. But if you care about the forced response, you have to use phi prime again and plug it into the formal expression. But that would be pretty straightforward to do. Then convert the solution to the original basis by saying, okay, we know x prime of t. Now we just can find x of t using the modal matrix to transform back to x. So that's one way to go, and that's a good way to go. So you could convert over to your primed basis, your diagonalized basis, solve for x prime, and then convert it back to x. Okay? That's totally valid. Or we can go a different route, which is common to do. Sometimes we prefer to transform the diagonalized basis state transition matrix into the original basis, okay? Which allows us to work not in the primed basis at all, really, except for just finding the primed state transition matrix and then converting it to our regular one. The real value that we're getting by going to one of the main aspects of the primed diagonal system is that we get this state transition matrix. So instead of actually going down in there to do everything in the primed diagonal system, solving everything down there, we're just going to dip down there and grab out the state transition matrix and then bring it up to our original basis. So sometimes I prefer to transform the diagonalized basis to state transition matrix into the original basis. The following is a derivation of that transformation. Beginning with the free response solution in the diagonalized basis. So let's see, where am I? Should probably catch up in my notes. And transforming the equation into the original basis, we find an expression for the original state transition matrix as follows. So we know that our x prime free response is, based on our previous derivation, phi prime of t times the initial condition in the primed variables. Right? Now, let's transform this into unprimed variables, okay? So we use the fact that x prime is equal to m inverse x. Times m inverse x of 0. So what we've done here is we turned the primed x's into regular x's, right? Now, if we left multiply both sides by m, this m inverse drops out, right? Becomes the identity matrix. And we're left with x free on the left-hand side, m phi prime m inverse x of 0. So this last expression is just a free response of the original basis state vector, right? So x equals something times the initial condition is this expression in the unprimed variables. So whatever this matrix is that multiplies the initial condition has to be the unprimed state transition matrix, the coveted unprimed state transition matrix. Therefore, we have this identity here. Phi is equal to m phi prime m inverse. It's a powerful result. It's the preferred method of deriving the state transition matrix for a given system. The eigenvalues give phi prime, right? Phi prime just being e to the lambda t. And the eigenvectors give m. So you find the eigenvalues and eigenvectors of a system, and you can write down its state transition matrix like that. So this is like the big payoff right here at 221. Question?
On the equation, they're not missing the times of any of x, are you? I'm just asking how we're...
Right, that's right, because we went from primed to unprimed here. So that's what the step was about, was taking this primed variable and turning it into unprimed, primed to unprimed. So yeah, you're right. So there's no primes in there. The only prime that remained is the one on the phi. So you guys ready for an example? You guys are like theoried out. You want a good old-fashioned example with numbers? What? Did I make a mistake? Actual numbers, guys. Okay. So for this state equation, so what's the order of this system? Second order system, right? It's a 2 by 2 A matrix, so it's got to be second order. It's always n by n. And we have the question before us of finding the state's free response to the initial condition that's given. So this is a common way to write a column vector without having to write it, taking up a bunch of vertical space on the page. So you write it with the transpose on it. So that's just saying x of 0 equals 2, negative 1. Okay, so what do we do? Sorry? Find our lambda. So our general idea is that we can find the free response from this expression, right? X free is equal to phi x naught. So all we need to know is phi. Once we have phi, we have our solution. So phi is what we're going for. And remember, we just learned this fancy new way to find phi. So all we need to know about the system in order to find phi is what its eigenvalues and its eigenvectors are. So we gotta do that. So we gotta find the A matrix eigenvalues and eigenvectors. Okay. Eigenvalues. Do you guys remember what the equation is? Determinant of lambda I minus A equals 0. And that's just going to give us our lambdas, right? We'll go through the details, but I know it's boring, so I apologize. Just for me, just going through the details. It's cathartic. Okay. So, determinant of lambda I minus A inverse. So I want to say, actually, let's compute over here, maybe. What is lambda I minus A? Okay. It equals lambda I, we need a 2 by 2 I, right? Because we have a 2 by 2 A. Negative 2, 2, 2, negative 3. And what do we have? Lambda plus 2, 0 minus 2, so negative 2. 0 minus 2, so negative 2. Lambda minus negative 3, so lambda plus 3. That's what I get. Is that what you guys got? Mm-hmm. I rely on you. You guys are better at this than I am. I mean, I know like the formulas and like the theories and the ideas, but like computing stuff, man, I've gotten really used to using computers for that. Okay. So I don't have to take in-class by hand calculation exams anymore. So it keeps you sharp doing that. Okay, so lambda I minus A. So now we need to find the determinant of that. So that is, remember this, so lambda plus 2 times lambda plus 3. So this times this minus this times that. It's like an x, right? Well, it's actually like that. Which I think is like a Darwin fish, maybe? I don't know. But I think that the other one goes this way. I look at bumpers sometimes. What can I say? So, lambda plus 2 times lambda plus 3 minus, so minus negative 2 times negative 2 equals 0. So expanding that out, I get a lambda squared, I get a plus 2 lambda, and I get a 3 lambda, so I get a 5 lambda. I get plus 6 minus 4, which gives me plus 2 equals 0. Okay. So you can solve this however you want. Lambda 1 and lambda 2. I get negative 4.56 and negative 0.438. Okay. Now, we have our lambdas. So what is our lambda matrix? Yeah, so negative 4.56, 0, 0, negative 0.438.
Something you didn't say earlier, because people are going to solve it differently. It doesn't matter which order you find lambdas in, as long as the vectors match the position where you put the lambda.
Exactly. So you have to be consistent. It doesn't matter which order you choose, just like with the state variables. It doesn't matter which order you choose, but you have to be consistent. So if you choose lambda 1 to be this one and lambda 2 to be that one, whichever m you get from plugging in this lambda, you got to call m1. whichever eigenvector you get, you got to call M1. And then that's when you got to call M2. Otherwise, you're in trouble. Okay. So the eigenvectors. You can already see this is going to be hard to get through. We learned how to compute eigenvectors before, so I'm going to skip this part and just say M1, because I want to get to the payoff, right? M1 equals, if I can read my own writing, any scaling of negative 0.781, where obviously this is an approximation, and 1. And M2 is equal to 1.28 and 1. Any scaling of that. So that means our modal matrix is whoops, 1.28, 1. Boom. Okay. Now all we need to do is find phi. Well, first we'll find phi prime, and then we'll find phi. So phi prime is easy. We could have found it after finding the eigenvalues, right? What is it? Well, I'll just write e to the lambda 1t, because lambda 1 is an ugly number, decimal number, so I don't want to write it out. 0, 0, e to the lambda 2t. Boom. And now we have and phi of t is equal to, from the expression that we just wrote, 221, it is m phi prime of t m inverse, right? And this is essentially just plug and chug. So I leave that to you. You just have to invert m, which this is pretty easy shorthand for a 2x2. So then our final solution, though, we don't want to go without doing our final solution. So free response, then we can use the nice formula x free of t equals the state transition matrix, which we just found, times the initial conditions, and this result plugs in there, and then our initial condition was 2, -1, right? So we compute it, and that's it. There's a little bit of like kicking around numbers there, right? But overall, not too bad. Yes, question?
How do we determine our initial conditions?
So that has to be, if you're designing a system, you have to choose what they are in a sort of physical sense, whatever makes sense. But in a problem like this, you'd be given the initial condition.
So for this, would you leave t as a variable when you're solving that?
Yes, so t is known for this expression because it's the initial condition at time equals 0. But this time is just t. So it's an expression that'll be a function of time.
I was talking about.
Okay.